Okay, good morning, everybody. So yesterday we spoke about developing mechanisms for small hydrocarbon species. So now I'm going to talk about mechanisms for larger hydrocarbon species. Okay, so the boundary between small and large fuel molecules is somewhat arbitrary, but C5 fuels have much more low temperature kinetics than C4, and C6 fuels have much more low temperature kinetics than C5. Okay, so C6 and larger molecules have lots of low temperature reaction pathways, cool flames, and lower octane number values than smaller fuels. Okay, so typically you can consider the boundary lying around C4, C5, in fact. Okay, this is just a figure. Well, this figure I got courtesy of Professor Tianfeng Liu. He worked with Professor Law here at Princeton, and they published an initial version of this figure in a PEX paper, I think around 2012. And it just shows you a plot of the number of reactions versus the number of species in mechanisms. And you can see here, clustered in this lower corner with smaller reaction mechanisms, those that existed up to before 2000. And then after 2000 up to more modern day, you can see that they've been growing in size. And why is that? It's because of computing power, essentially. Okay, so this is just a plot of calculated, calculations per second per constant dollar versus year. And you can see that this is fairly linear. Okay, Moore's law. All right, and so really the mechanism, chemical kinetic mechanism development and size has reflected the increase in computing power. Okay, and they're just some of the citations. Okay, so as I said, I think this should be 8 actually, but I had 8 and 20. Okay, so you have that order, 30 and 200 for methane. For propane mechanisms, maybe 100 species, 400 reactions. And oftentimes now, so for something like cetane, C16, H34 molecule, you're talking about 1,200 species, 7,000 reactions to describe it. Okay, so they get more and more complex the higher the hydrocarbon size. Okay. Okay, so, and yesterday I was showing this for nearly all hydrocarbon oxidation, no matter how large or small the fuel molecule, at high temperatures, the reactions of the hydrogen-oxygen system have the greatest sensitivity, controlling the overall rate of reaction. This is true in flames, detonations, shock tubes, and many other practical combustors, speciation measurements in flow and just stirred reactors, and so on. Okay, but there's one underlying principle that I'd like you to remember. And this is a slide courtesy of Professor Tiziano Faravelli at the Politecnico di Milan, that at low temperature, because of the energy, the activation energies involved, okay, at low temperature, we have hydrogen abstraction from the fuel forming a radical, and that radical adds to molecular oxygen, forming oxygenated species, okay? And then these oxygenated species finally undergo pyrolysis to give smaller products. Okay, so that's at low temperature. Okay, so you get, at low temperature, you get oxidation first, followed by pyrolysis. Okay, but at high temperature, it's the opposite. At high temperature, you're at temperatures that are high enough to overcome the activation energies required for CC bond cleavage, typically CC. Okay, and CH, but CC. So you get pyrolysis first, then you get smaller species, and then those smaller species undergo oxidation to products. Okay, so the mechanisms are a little bit different, and it's a nice simple graph or slide to show that, illustrate that point. Okay, so I showed you this earlier, I think yesterday. So if we look at the conversion, we have the low temperature chemistry. So if we look at reactivity at low temperatures, we have hydrogen atom abstraction from the fuel by hydroxy radicals I introduced this yesterday. So these hydroxy radicals are coming from this process, the chain branching process at high temperature. Okay? So primarily, reactivity is controlled by abstraction by hydroxy radicals. We generate the alkyl radical. The alkyl radical adds to molecular oxygen, forming alkyl peroxy radicals, and they can undergo isomerization to hydroperoxy alkyl radicals. Then we have a second addition to molecular oxygen, forming hydroperoxy alkyl radicals, and then they undergo a second isomerization, forming this intermediate species, but actually this is very short-lived, okay? This goes on to cleave to give this carbonyl hydroperoxide species plus OH, okay? And then this carbonyl hydroperoxide species breaks the OO bond. We get this carbonyl alkoxy radical plus OH, okay? And as I said yesterday, from one fuel radical, if we go to chain branching, we get 1, 2, 3 reactive radicals. So it's a chain branching process. From one radical, we get 3, and it's chain branching, okay? And this is illustrated here. So we have low activation energy barriers. So processes. So so we abstract a hydrogen atom from the fuel. The energy barriers for that process are low, okay? There is no energy barrier for alkyl radical addition to molecular oxygen, okay? And I'll be talking about that a little later, okay? So we get an alkyl peroxy radical. And now we do have energy barriers for these isomerizations, okay? Forming the hydroperoxy alkyl radicals, okay? So at low temperatures, temperatures from above 500 to 850 Kelvin, this is the chemistry that controls reactivity, okay? So depending on the type of fuel, okay? Now, one thing, there has been evidence of further additions to molecular oxygen, okay? But if you look at these publications, so these are two that were published 2017, 2018. It was work that was led by Mani Sarati at KAUST, and other co-authors were involved. But so there is evidence that there are, so once we form these radicals, then we have a third addition to molecular oxygen and possibly a fourth, okay? But actually, the concentrations of the species stemming from this are 1/10 the concentrations of the species stemming from the second isomerization. So that, 90% of the chemistry or more is captured with the first and second addition, okay? So in my opinion, this is less important. Okay, that's just my opinion. Okay. Now let's look at negative temperature coefficient regime, because actually, if we look at reactivity of alkanes, and I'll be showing this, okay? If we had just low temperature kinetics, okay, and we looked at conversion versus temperature, what we would see is a conversion that would follow that blue curve, okay? If we just had high temperature kinetics and we followed the conversion, all we would see is this red curve, okay? And typically for alkanes, we don't see that. We see this negative temperature coefficient behavior. So actually, we see this reactivity. So we start at low temperature, no reactivity, okay? Due to this low temperature chemistry, we get reactivity up to this point. Then we see actually a decrease in reactivity, and then we fall onto the high temperature kinetic. So there is a transition from low to high, okay, which results in a decrease in reactivity. So what's causing that? Okay, well, all these reactions cause that, okay? So, but really, in my opinion, the fulcrum lies here at the hydroperoxy alkyl radical, okay, for low temperature, for this negative temperature coefficient behavior, okay? And I'll talk a little bit more about that in a few more slides, okay? So we reach this alkyl peroxy radical, and this alkyl peroxy radical can undergo a concerted elimination reaction, forming an olefin plus HO2. Okay? Just bear with me. I know it's a little bit confusing and it's a bit esoteric in that we're just naming these and that we have RO2 and QOH. What do these molecules look like and so on? I'll have some examples later and we get more familiar. I'm just introducing it now, all right? Or the alkyl peroxy radical can go on to form a hydroperoxy alkyl radical, which is an internal H atom isomerization, okay? And what happens here, this is really critical in my opinion, okay? If these species, the hydroperoxy alkyl radicals, add to molecular oxygen, they go on essentially to chain branching. However, if these species generate a cyclic ether plus OH, beta scission products, or the RO2 gives an olefin plus HO2, then you get this negative temperature coefficient behavior. Why? Because if we look at it here, I've put a radical site on the radicals. There should be beta scission products, which involves one radical. Okay, so if this hydroperoxy alkyl radical species undergoes a propagation reaction, in other words, the RO2 gives olefin plus HO2. This hydroperoxy alkyl species gives a cyclic ether plus OH, or gives beta scission products. We get one radical from one fuel radical. So we have a flux this way. Okay? We get one fuel radical, we get RO2, we get a hydroperoxy alkyl radical, or RO2 gives olefin plus HO2, but one fuel radical goes to here. Okay? We get one radical from one fuel radical. That's not branching, it's propagation. And so reactivity decreases relative to lower temperatures. Okay? So at lower temperatures, these hydroperoxy alkyl radicals add to molecular oxygen and go on to give products. And in branching, give 3 reactive radicals in chain branching. Okay? But at these intermediate temperatures, here, what happens is these hydroperoxy alkyl radicals, these reactions, and from RO2 to olefin plus HO2, or hydroperoxy alkyl radical, essentially to cyclic ether plus OH, lead to propagation, not branching. And the reactivity of the system decreases. And then at higher temperatures, again, at intermediate temperatures, you have RO2 giving us olefin plus HO2 is important, and the hydroperoxy alkyl radical giving us cyclic ether plus OH is important, right? And again, we're getting one radical from one radical, not branching, therefore it's less reactive. Okay, so if we look at this profile, I showed you, I think day 2, on Tuesday, I showed you this graph, okay? And again, we have N-butane oxidation in air at 20 atmospheres. This is lean, stoichiometric, rich. And we have 3 different regimes. So at low temperature, the reactivity increases to this point because we form an alkyl radical, it adds to molecular oxygen, we get alkyl peroxy radical, isomerizes to hydroperoxy alkyl, and goes on to chain branching. We get a carbonyl alkoxy radical and 2 OH radicals, chain branching. Okay, at intermediate temperatures, so in this sphere here, up to this point, okay, we have different chemistry. So we have, and we spoke about this yesterday, H adds to molecular oxygen, but we get propagation, not branching. We get HO2, okay? And then that HO2 abstracts a hydrogen atom from a stable molecule, mostly the fuel, but also sometimes high concentrations of a major intermediate, okay? And gives an alkyl radical plus H2O2, hydrogen peroxide, which then decomposes into 2 hydroxy radicals, okay? But another important part here, and I'll explain a little later to this mechanism, is actually the alkyl radical does add to molecular oxygen still in this temperature regime, and it's worth remembering this to give alkyl peroxy radicals. And those alkyl peroxy radicals then undergo concerted elimination, forming olefin plus HO2. So this is another route to HO2 formation. And then HO2 abstracts a stable molecule, giving you H2O2, which gives you 2 OHs. Okay? So this is another important mechanism for HO2 formation at intermediate temperatures. Okay? It's not just H plus O2 plus M. Okay? It comes from fuel radicals. Okay? And I think that this proves it, because if we look again at the reactivity, the relative reactivity, 5.5, 1, and 2. What did we say is really changing if you look at these, the concentrations of the mixtures? What really changes? The oxygen concentration actually doesn't change very much. It's the fuel concentration. Okay? So if your fuel in air, 5.5, fuel in air 5.1, fuel in air 5.2, actually the oxygen concentration is pretty constant at around 20%. What's changing is your fuel concentration actually. Okay? And so, in other words, your alkyl radical concentration will be then proportional to the concentration of the fuel. Okay? And so your alkyl radical concentration is increasing by a factor of 2 each time. And you can see up to this point, rich mixtures are faster. Okay? So in other words, the more alkyl radicals you get, the more RO2 you're going to get, even up to 1200, 1250 Kelvin at 20 atmospheres. The more RO2 you get, then the more olefin plus HO2 you're going to get. The more HO2 you're going to get, the more H2O2, the more OH, and the more reactivity. Okay? So rich mixtures are faster even in the intermediate temperature regime. Okay? And it's due to this added mechanism. Okay? And then at high temperatures, over here, we have the fuel typically undergoes unimolecular decomposition reactions. The radicals formed then decompose to smaller olefins and smaller radicals, and those smaller radicals eventually produce methyl or hydrogen atoms or ethylene and so on. And we get H plus O2 giving us O plus OH, and we have methyl plus O2 giving us formaldehyde plus OH. And a lot of the reactivity is stemming from those reactions. Okay? Okay, so prove it. And this is actually proof positive. And this is actually just published, we'd say, relatively recently at the proceedings in 2011. It's a really nice paper which proved the three different oxidation mechanisms. So this was taken by Professor Maruta's group in Sendai in Japan in a microflow tube. And what they looked at the oxidation of N-heptane at low, intermediate, and high temperatures. Basically, N-heptane oxidation flowing through the tube, in the microflow tube. And what they looked at light emission, and they see three distinct light emissions from reactivity. And so there's three distinct regimes of reactivity observed. Okay? So fairly low light emission, not very intense, not very intense, and very intense at high temperature light emission. Okay? And so Charlie Westbrook thought those experiments were really cool and then simulated that. So if you simulate N-heptane, okay, it has a research octane number you all know of 0. Okay? So here we plot temperature versus time. That's the red line here. So the temperature is increasing. And it really doesn't tell you very much. Okay? But if you look at the heat release rate versus time, you see very clearly three distinct regions. And a very intense heat release rate at high temperature. Okay? You have this low temperature heat release rate, intermediate temperature heat release rate, and high temperature. Okay? So that very much corresponds with what was observed experimentally in those experiments. Okay? And this is exactly what's happening. So you've got the low temperature kinetics, the intermediate temperature kinetics, and the high temperature kinetics all combining to give this heat release rate curve. Okay? All right, so we focused yesterday primarily on the high temperature kinetics. Okay? So now, first I'm going to switch back to the intermediate temperature chemistry, and then later we'll do the low temperature chemistry. All right? So, and these are the important reactions at intermediate temperatures. And so I spoke a bit about this yesterday, so I'm not going to talk much about this in, today, the H plus O2 plus M reaction, but I'll talk about the others and where we get the rate constants for those reactions, okay? Again, if we're going to accurately predict the reactivity of any fuel in this regime, be it an alkane, alkene, oxygenated hydrocarbon, we're going to have to understand their reactions, okay? So the fuel reaction with HO2, the alkyl radical reaction with molecular oxygen, and this concerted elimination reaction, okay? Okay, so these are the important reactions, just highlighting them again. So now I have in bold, I don't know, it's not easy to see, but this RO2 giving you olefin plus HO2. So where do the rate constants come from then? Okay, before I go to that, this is just illustrating the importance of the concerted HO2 elimination reaction. I think it's a really cool slide, okay? Again, this was published by John Bugler working in my group in 2016. He actually did a lot of very nice work, John. Okay, and this is just showing you the reactivities of N-pentane, isopentane, and neopentane. And you can see they have different research octane numbers, okay? A good rule of thumb is that the more highly branched a fuel, the higher the octane number, okay? But actually it isn't true here for neopentane. So if you compare N-pentane and isopentane, you can see the octane number changes from 61.7 to 92.3. Okay, so it's branched. You'd expect the research octane number of neopentane to be even higher, 100 and something. Okay, it's not actually, it's 85.5, which is a little bit strange. Okay, so these are ignition delay times that were measured in both a rapid compression machine, which are the open symbols, and shock tubes, which are the solid symbols, and a shock tube, okay, taken in my lab, okay? And you can see here the black symbols are for N-pentane, the blue symbols are for neopentane, and the red symbols for isopentane. And what you see is possibly what you'd expect in terms of reactivity for N-pentane and isopentane. At low temperature, N-pentane is quite a bit faster than isopentane, okay? And then you go into the NTC region, N-pentane decreases in reactivity, you get that negative temperature coefficient behavior, okay, due to the QOH undergoing propagation rather than branching, adding to molecular oxygen, and then you fall into the more intermediate high temperature regime, okay? And N-pentane and isopentane are pretty logical. Isopentane is quite a bit slower than N-pentane because of its branching, and I'll talk about that later, okay? And then at intermediate and higher temperatures, both of the fuels are very similar in reactivity. It's only here at lower temperatures that there's a very big difference in reactivity, okay? Neopentane is very much different, okay? Neopentane has, again, it's very slow at lower temperatures, as slow as isopentane. But then in this intermediate temperature regime, neopentane doesn't slow down like isopentane at all. In fact, it becomes almost as fast, okay, as fast as N-pentane. And then at these intermediate temperatures, going into the intermediate high temperature regime, neopentane is actually much slower than the other two. And even at higher temperature, you can see it's consistently slower. Okay, so what's going on with neopentane relative to the other two? Okay, so what happens is this, okay? Okay, here we have neopentane, okay? And at high temperatures, it can undergo unimolecular decomposition. So we can get terp-butyl radical and methyl radical, okay? Or at low temperature, it undergoes hydrogen atom abstraction by hydroxy radicals, okay? It gives you form this neopentyl radical, and that can undergo, at high temperatures, can undergo beta scission, giving you isobutene plus methyl, okay? That's okay. But at low temperature, okay, that adds to molecular oxygen, forming this neopentyl peroxy radical, And that neopentyl peroxy radical, can I summarize to this hydroperoxy neopentyl radical? Okay, so you can see here the hydrogen atom, we have a 1, 2, 3, 4, 5, 6 centered transition state leading from the alkyl peroxy radical to the hydroperoxy alkyl radical. Okay? The numbers here are showing the flux. So if we take 100 fuel molecules at these temperatures, and this flux analysis I actually published 20 years ago in a paper, right? It was data taken from a flow reactor, actually with, I think it was Nick Cernansky's flow reactor, okay? And what I did was I did a flux analysis, just to go back a little bit. I did a flux analysis here at the top of the NTC region, okay? Where we were getting the least reactivity just before it turned over, okay? And so at the top of the NTC region, okay, of 100 molecules that would undergo abstraction forming an alkyl radical, okay, 89 of them form RO2 and 85 form QOH, okay? So even at the top of the NTC region, we're getting a lot of low temperature chemistry, okay? So now we have 85 out of 100 going to hydroperoxy alkyl radical, okay? But actually, and then a small amount, about 10% undergo beta scission here, and only about 4% form this neopentyl hydroperoxide, okay? Don't worry about that, okay? But it's just showing where it's all going, okay? But this is where all the business is, okay? So this is our QOOH, okay, that I was talking about. So this is RO2, this is QOH. So now, at the top of the NTC region, what's happening to QOH? Okay, if we look at it, only 38% of these are adding to molecular oxygen of the overall flux. Okay, everything is normalized. Okay, so of 100 fuel radicals that are formed, only 38.4 are adding to molecular oxygen. All right? But now we have a substantial portion of these forming the cyclic ether plus OH. Okay? 35, 36 in 100. Okay? And then about 10 are giving these beta scission products. Okay? Isobutene plus formaldehyde plus OH, or this hydroperoxy alkenyl species plus methyl. Okay? So this is the cyclic ether, and these are the other beta scission products that I was talking about earlier. Okay? So this is, what is it? 35, 45, 46%. So 46, a large portion of the hydroperoxy alkyl radical is going to propagation, not branching. Okay? So if I just go back here, and if I did a flux analysis here, what we would see, to this point, we're getting most of the hydroperoxy alkyl radicals will be going to branching, adding to molecular oxygen and pursuing that route to branching. And then more and more, as we go higher in temperature, of these hydroperoxy alkyl radicals are going to form cyclic ethers and these other beta scission products. Okay. The reason that this is much higher than this is because the energy barrier for the formation of the cyclic ether is lower than it is to form these beta scission products. And so this will be more important at lower temperatures, and at the top of the NTC, it would be slightly less important, with these becoming more important, because the activation energy barrier is more easily overcome. All right? But if you want to put maybe a red box around this species and highlight it, and I would call it the fulcrum. It's really the fulcrum of whether you're going to get chain branching or propagation. and it's responsible for negative temperature coefficient behavior. Okay? This species here in neopentane. Okay. One thing, it's a little Henry story. And do I have it? I don't. Okay? But I'll tell it anyway, and I'll finish it out. Okay, so here then, the hydroperoxy alkyl radical can add to molecular oxygen, and we get this peroxy hydroperoxy alkyl radical. Okay? And that then undergoes a second isomerization, abstracting this hydrogen atom, forming this is the radical, which very quickly decomposes to give our carbonyl hydroperoxide plus OH. And that carbonyl hydroperoxide then cleaves the OO bond, giving the carbonyl alkoxy radical plus OH. So here we're getting our 1, 2, 3 radicals from one fuel radical. And that's the branching process. Okay, so once we arrive here, and this is something published many years ago, there were some experiments performed by Ray Walker. He did a lot of very nice work in the 70s. And he had this, a closed reactor where he did experiments in hydrogen and oxygen, doping that with a little bit of fuel. So he looked at that, for instance, with neopentane. And what he measured a pretty high concentration of acetone as one of the primary products at low temperature. But nobody could understand or predict where the acetone was coming from. Okay? So actually, and because they didn't follow the chemistry down. Okay? So actually, in the paper in 1996, I actually found out where it was coming from. Okay? And it's coming from here. So now we form this radical, and that can be a decision to form this radical. So this molecule here plus formaldehyde. Okay? Sorry, acetone, I should say. Sorry, no, formaldehyde. Excuse me. Okay, and I haven't got the slide, so I'll just show you here. And then this radical okay, can now add to molecular oxygen again. Okay, so we get this radical, okay, and then this hydrogen atom is quite weak because it's an aldehydic. Okay, so that isomerizes, we get this species plus that. And anytime you have a carbonyl radical, the radical site on the carbonyl, this actually decomposes and it gives this species plus CO directly, which then this undergoes by decision to give acetone plus OH. Okay, so it was from that radical there that acetone was being formed. Okay, because there were all sorts of papers at the time saying that there might be a diradical formed, and it was through that diradical that the acetone was being generated. Okay, but this actually showed the mechanism for acetone formation. So you get by decision of that species forming acetone plus OH. Okay, it was just a nice thing. So you have to follow the whole thing down, look at the logical chemistry that can happen, and you can get to the products, okay, the details. So if I go back here, so we do get negative temperature coefficient behavior for neopentane. But you can see, look, it's not nearly as pronounced as it is for N-pentane and isopentane. Okay? And actually, neopentane falls on top of N-pentane here coming out of the NTC region. Why? Because actually, one reaction pathway that is very important for concerted elimination, for NTC behavior is the concerted elimination. So RO2 giving olefin plus HO2. And you cannot get that for neopentane. Okay? You cannot get the concerted elimination. So what is the concerted elimination? Let me try and see. So for N-pentane, for instance, okay, we have the most easily abstracted hydrogen atom is a secondary. So I'll draw it here. Okay. And we have this radical. Okay? And now, if we abstract a hydrogen atom on this carbon here, okay, we get this species as an intermediate. Okay? This would be an RO2 to QOH. Okay? But now, this can cleave this CO bond, okay, to give an olefin, sorry, plus HO2. Okay, so this electron moves in here, this electron moves in here, and that electron moves out. Okay, if that makes sense, and you get 2-pentene plus HO2. Okay, and that can okay. But the concerted elimination, when you, let me try and draw it again. Okay, so we add molecular oxygen, and we go through this intermediate step. So we have 1, 2, 3, 4, 5. We have O, O. Okay, we have this intermediate, okay, a transition state, but there's so much energy in the system that when the hydrogen is bonded here, we've got sort of a half bond. Okay? And there's enough energy in the system that we get a concerted elimination. We don't arrive, as I just depicted, at the hydroperoxy alkyl radical and then beta scission. Okay? There's enough excess energy in the system that the beta scission can happen immediately. Okay? And so what this gives directly is that species plus HO2. Okay? So this is the RO2 concerted elimination to give olefin plus HO2. Okay? So typically for these 5-membered rings, there's enough excess energy in there that it just goes directly to olefin plus HO2. Okay? It doesn't give the QOH. Okay? However, if we take neopentane, okay, we abstract a hydrogen atom, we add molecular oxygen, we have this species here. And now, we don't have a hydrogen on the carbon here to have a 5-member transition state ring. So we can't get an olefin plus HO2 from neopentane. It just can't happen. Okay? We can abstract a hydrogen atom from one of these carbons. Okay? There's hydrogens here. But if we do that, we get that radical plus. Okay, but this is a 6-membered ring. 1, 2, 3, 4, 5, 6-member transition state ring. And we don't get, if we had a beta scission here, we would get isobutene plus formaldehyde plus OH. It's not a C5 olefin. We cannot get a C5 olefin from neopentane. Okay? It's not possible. And so, for N-pentane and isopentane, we can get these concerted elimination reactions. Those concerted elimination reactions contribute significantly to negative temperature coefficient behavior. And you can see very pronounced negative temperature coefficient behavior. So as we go higher in temperature, the reactivity of the system decreases significantly. Okay? And you see that very much so for N-pentane, a little bit less for isopentane, but it's still significant. And you don't see it at all for neopentane. You do see some NTC, right? You do see some NTC, and that's due to those propagation, the cyclic ether and the other beta scission products. Okay? But a significant contributor is this concerted elimination reaction. Okay? And it's not present in neopentane. But because it's not present, okay, we get more reactivity in the NTC region, but we actually get less reactivity in the intermediate temperature regime. Why? Okay, because we're not getting RO2 giving us olefin plus HO2. And what did I say about HO2 in intermediate temperature chemistry? It abstracts a hydrogen atom from a stable molecule, giving you H2O2, which gives you two OH radicals. Okay? So if you get HO2 formed at intermediate temperatures, you get chain branching. And that leads to higher reactivity. So you get somewhat similar concerted elimination in N-pentane and isopentane, but you don't get it at all for neopentane, and hence its reactivity is much lower in that intermediate temperature regime. Okay? Because you're not producing HO2 from that concerted elimination for neopentane. Okay? So there's a lot of very rich chemistry here. Now, at higher temperatures then, in here, you're also getting a lot of isobutene. And I'll show you a slide tomorrow which shows the relative reactivities of isobutene, propene, and other olefins. Okay? Either today or tomorrow. I think it's tomorrow. Okay? And you'll see what I mean about the isobutene inhibiting reactivity. Okay? So you get a lot of isobutene from neopentane, which you don't get from N-pentane and isopentane. Okay? And that's decreasing reactivity up here. But the reason that this is slower here is because we're not getting any concerted elimination. Okay? So concerted elimination, the rate constants then for concerted eliminations are very important to predicting fuel reactivity in the negative temperature coefficient region or at intermediate temperatures. But actually, the rate constants aren't well known. Okay? There have been some calculations. So it was actually Quelch in 1994 that first proposed that ethyl plus O2 actually can go directly to ethylene plus HO2 via cyclic transition state. Something like I've just depicted here. All right? And then Miyoshi used variation transition state theory to look at a few different species plus O2 and published on that in 2011 and 2012. Okay? And around the same time, Tony Dean, Stephanie Villano, were working essentially, largely with Heinrich Carstensen and Tony Dean at Colorado School of Mines, published calculations on 23 different straight and branched alkyl peroxy radicals and came up with rate constants. And also Franklin Goldsmith working with Bill Green and Steve Klippenstein looked at the propyl plus O2 system. Okay? But I think we need much more studies of the rate constants of the reactions of these to get a much better handle on accurate rate constants for these. Okay? They're important. Okay, so there too. Another reaction class that's important at intermediate temperatures is fuel plus HO2. Okay? Because now you have the HO2 produced from that concerted elimination reaction. What is the rate of abstraction? Okay? And actually, there's few direct measurements of H-atom abstraction by HO2. There's a lack of suitable precursors. So researchers like Professor Hansen can't get a precursor for HO2 formation that he can then look at the rate of reaction with a stable molecule. Okay? Jemmy Alade and co-workers did look at formaldehyde plus HO2 using flash photolysis. And I mentioned Ray Walker a little earlier. He did a lot of indirect relative rate measurements of rate constants for abstraction. Okay? And it culminated, this is a nice paper. You should maybe look at it. in a review article of alkanes, aromatics, and related compounds in 2002. Okay? There have been, so the community is making progress on HO2 and actually recording it. So up to, we'd say, just early this decade, there were no quantitative measurements of HO2. Okay? So even quantitative measurements of HO2 will be a good constraint on a mechanism. So if HO2 is important and we're able to predict it pretty accurately from the measurements, it's an indication that the mechanism is getting the production and consumption of HO2 correctly. Okay? So that's good. Any information like that is helpful. All right? So, so Block A, working with Frédéric Batin-Leclerc and Christa Fitchen, first published fluorescence assay by gas expansion measurements of HO2 radicals in 2013. Okay. There was a dual modulation Faraday spectroscopy study published by, which is this 6 and 7. It was actually Igwang Ju's group here at Princeton, okay, on HO2 concentrations. And cavity ring down spectroscopy study was performed by Philippe Dagau's group at the CNRS in Orléans. Okay? So all of these were published within a few years of one another, 2013, 14, 15. Okay? And these have been an advancement in our understanding of HO2 chemistry and basically intermediate temperature kinetics for all fuels. Okay? So, and the measurements are very useful, as I said, in assessing the mechanism performance, whether the mechanism's predicting the formation and destruction of HO2 correctly. All right. Okay. And here you see, this is a sensitivity analysis taken from a paper published from my group on methanol oxidation. And you see here at 40 atmospheres and 890 Kelvin, the most important reaction enhancing reactivity is abstraction from the fuel by HO2. Okay? It's the strongest. It's even more important than H2O2 decomposition. All right? So, but these are actually rate constants calculations and rate constants used by versus inverse temperature given in the literature. So here's a high-level calculation performed by Stephen Klippenstein. This is a rate constant from Maleku and Trular. This is one calculated by Rane. I hope I'm correct spelling or pronouncing that correctly, in 2011. Okay? And you can see, and actually this is, we'd say, an optimized, using both direct and indirect measurements, rate constant by Karsten Olm et al. It's from the same group as I was talking about yesterday for optimization of a hydrogen mechanism. They optimized a methanol mechanism. Okay? And so this red line is an optimized rate constant from both direct and indirect measurements. And you can see that there's quite a large spread in the rate constant calculations, maybe a factor of 5 to 10, okay, which is very large. Okay, so even among ab initio calculations, there's quite a bit of disagreement. I spoke with Stephen Klippenstein about this, and he said, look, he doesn't think that he did anything wrong, can't see what he did wrong in his calculations, and so he's not quite sure what the problem is here, right? But there is. But, and this is just then showing you the predictions with using the different rate constants, okay, from a mechanism. So if you use the faster rate or the slower rate, and one's in between. So this is A, B, C, D on the next slide. So if you use Rane rate constant, the mechanism's slightly fast against the data. Okay? If you use the Olm rate constant, it's about right. Okay? If you use the Aleku rate constant, it's getting too slow. The predictions are too slow. And if you use the Klippenstein number, it's way too slow. Okay? So which one do I choose to use? All right? So this is what we choose to use. But there's no good reason why we should use that. Okay? I trust what Stephen does, and in calculating, he said he doesn't see what he did wrong. But these are ignition delay time measurements that we performed in our lab versus inverse temperature. Okay? And again, like, they're very sensible. They're not properly marked on this. I apologize. But, you know, this will be probably lean stoichiometric rich, okay, at a certain condition, okay, of pressure. But anyway, that's not the point. It's just showing you the choice of ray constant, okay? But it's showing you, though, the sensitivity the system has to fuel plus HO2 in this regime. It's hugely sensitive. And so we really need very accurate ray constants for fuel plus HO2 and the ray constants for the generation of HO2 at intermediate temperatures. And what I'm trying to say is, ultimately, as a community, we need to be able to do more sophisticated experiments so that we can generate precursors that can produce HO2 so that we can actually measure ray constants of fuel plus HO2. We need to get more sophisticated ab initio calculations that we can calculate them more accurately, okay? But it's certainly an area of uncertainty within the community currently, okay? Fuel plus OH is much better understood. And I'll be talking about that either later today or tomorrow, okay? Okay, I've said all of this there, so I'm not going to repeat myself on that slide, okay? So where currently, and actually there's been few studies overall by the community. You'd be surprised at how the dearth of information that's available, okay? So Carstensen and Dean, the same Carstensen and Dean that I spoke about that worked with Stephanie Villano earlier, okay? They published ray constants for abstraction from methane, ethane, propane, and butane for HO2, okay? And recognizing the importance of this, I actually was asked to, we had a project funded, and I went to work with Wim Klopper's group in Karlsruhe Institute of Technology, I don't know, 10, 15 years ago now. And we calculated at a very high level the ray constant for abstraction from methane, okay? And then we used density functional methods to compare with the high-level coupled cluster calculations to see which one came closest. And we used that to calculate ray constant for abstraction from ethane, propane, and butane and isobutane, okay? And these agree well with the determination. So these single points that I have here are typically Ray Walker, Baldwin and Walker derived ray constants from relative rate measurements, okay? The solid black lines here are the calculations that we performed, and the red lines here are from Carstensen and Dean. So again, the ab initio calculations are, the Carstensen and Dean are always maybe a factor of 3 or 4 faster than what we calculate. Ours, you could argue, well, here he's closer, here we're a lot closer, here he's closer. Who knows which is right, okay? But we're typically slower than his calculations, the Carstensen and Dean calculations, okay? So we need more information on fuel plus HO2 is the bottom line, and it's important, okay? And you can see here, so this is an old sensitivity analysis taken from the paper we published in 2002 for isooctane. And one thing I want to point out here is, well, 2 things I want to point out. One, sensitivity to alkyl radical decomposition at low temperature, okay? So alkyl radical can decompose or can add to molecular oxygen. If it adds to molecular oxygen, then you get the low temperature chemistry is important, okay? But if it decomposes, it can't add to molecular oxygen, okay? So it's competing with that, inhibiting reactivity, okay? Another thing, though, that I'm highlighting here, yes, you see, again, at intermediate temperatures, and so A, 25 Kelvin, 1,000 Kelvin. Remember, we're at 40 atmospheres here. Okay? So the intermediate temperature kinetics is still important up to 1200 Kelvin. All right? And we see fuel plus HO2 still important. But actually, and fuel plus OH, less important actually than fuel plus HO2 in this regime. Okay? But surprisingly important is fuel plus CH3O2, methyl peroxy. Why? Why for isooctane, fuel plus CH3O2 should be important? Okay? So I haven't been talking about this at all. This is kind of out of the blue now. I was talking about fuel plus OH. Now I've been stressing fuel plus HO2 because of concerted elimination and producing HO2. But now we have fuel plus CH3O2. Where is that coming from? Well, you get, yes, you get CH3, the radical adding to molecular oxygen getting CH3O2. That's correct. But where's the CH3 coming from then? Pardon? The beta decision. Well done. Okay? So you won't see this for an N-alkane very much. Okay? But for molecules that can decompose to give you lots of methyl radicals, you see importance of fuel plus CH3O2, and then CH3O2 plus methyl, giving you methoxy plus methoxy. That comes in and becomes important. Okay? So for molecules that are branched, that can produce lots of methyl, you do see sensitivity to CH3O2. Okay? So considering fuel plus CH3O2 kinetics is also important for these branched molecules. Or dimethyl ether isn't branched, but dimethyl ether also produces lots of methyl radicals. Or methane at low temperatures will produce lots of methyl radicals. Okay? So CH3O2 kinetics is important there. Okay, so, and it's through this mechanism. So we have CH3 plus O2, this is what you said, methyl peroxy, that can abstract a hydrogen atom from a stable molecule, giving you methyl hydroperoxide, and methyl hydroperoxide can then give you methoxy plus OH. Okay, so that's a system. So actually, about the only studies that have been performed on this were also performed by Carstensen and Dean. They looked at abstraction by H, methyl peroxy, and ethyl peroxy on methane and ethane in this study. And also then, they extended that in a further study at the symposium in 2007, looking at other species also. Okay. Okay, but other than that, there's been very few studies, and the community needs more study of those. Okay, so now that's a good place for us to take a break, because now we've spoken about high temperature. I've spoken about the important reactions really at intermediate temperature, and now we're going to talk about low temperature chemistry. Okay, so let's take a break.